This is my lesson 46. 45, we had a little issue with the S8050 transistor. It wasn't able to do the job. It's not adequate to run this motor. So we did it with a MOSFET on lesson 45. Here on 46, we're going to contrast them. We got a bipolar transistor here, 120, TIP 120, and we're going to kind of contrast that against the MOSFET. We have a MOSFET here, another MOSFET we're going to use. It's rated for 5 amps, but like most of the transistors and MOSFETs, that's if you can keep them cool enough to run at that high of a current. This particular one, we can look at the data sheet and kind of gives us a calculation of what this can handle without a heat sink, which we're going to try now. It looks like if we look on this curve, collective versus voltage across the collector emitter, at 2 amps, we hit the line saturation because we're going to use this as a switch, so we're going to be working in the saturation region. So at 2 amps, 1 volt, P equals I times Z, or sometimes we call it P equals I times V. It should stay fairly cool until it gets close to 2 amps. So let's run it up, and we're at 5 volts across the motor in the power rail. Looks like also by this indication, we're going to be dropping 1 volt across the collector emitter. So looks like the motor is only going to see about 4 volts. So let's run it up. On our kit, the power supply that's included in there, that'll only give you 1 amp, but we've had a little bigger power supply here just for this test. Bringing it on up. Okay, we're at 1 amp. Doing well. Still cool. 1 amp. I don't think you probably shouldn't run these motors more than 1 amp anyway, so we're going to go a little farther, but in actuality you probably shouldn't. That motor seems like it starts to get hot above 1 amp. Transistor's doing well. Okay, let's bring it all the way up to the top. Full speed. Okay, 1.3. We probably won't get 2 amps because we're dropping 1 volt across the transistor. It looks like we're going to top out at 1.78 amps. Oh yeah, it's getting hot as hell here. Hot as a pistol. It's probably within its limits, but it's right at the top. It's probably about 1.6 watts, and we're limited to 2. So we'll back it off. Yeah, so back it off. And we'll take that guy out. It's still a little hot there. Take it out. And we have a TIP 120 with a heat sink. And we'll throw this guy in. Get it right on the right pins. The thing's still got power on it, so. Okay. Okay. Run it up. Now this one should run cool at the top. I'm going to just run it right up to the top. 1.87. And probably without a heat sink, you probably shouldn't run the TIP 120 past maybe like 1.5 amps without a heat sink. Yeah, nothing. It's cool. Let's see what the MOSFET's going to do here. We're going to take it all the way up. It shouldn't break a sweat on this. Let's get up to around about 10 amps without a heatsink. Since we don't have that voltage drop, it's going to go all the way up past 2 amps. We don't have that voltage drop issue that we have with the transistor, so it's getting the full 5 volts. And we're going to leave it up there, see how it runs. 2 amps, 2.12 amps. Very little voltage drop. It's getting the full 5 volts. Not breaking a sweat. Can't feel any heat. MOSFET's the way to go. Here we have our 2 test circuits. The TIP 120. You can get these are readily available as low as 30 cents a piece. Here we have our MOSFET. This particular model runs about $1.30, $1.50. Mauser DigiKey. And determining our max power without a heat sink, we have to get some information from the data sheet, especially the maximum junction temperature. This is the ambient temperature, and this is the thermal resistance. We have to get those values for each for the transistor and for the MOSFET. In this case, for our TIP 120, we do the max power without a heat sink to watts. Then we calculate our actual operational power, 1.658, and that's lower than what max is. So we're good to go without a heat sink with that operational value there. That brings our junction temperature to 128.68, and that's less than the maximum junction temperature of 150. So we're good to go there. And then with our MOSFET, same thing. We make the calculations, the max power without a heat sink. Then we look at our operational power. We can get this RDS on from the data sheet. In this case, with a 4.5 gate voltage, the worst case is 16 milliohms, or 0.016, and that ends up to be about 42 milliwatts. That'll bring our junction temperature up to 27.6, and that's the magic of the MOSFET. We're only operating a very low power for that amount of current, only 15% of max with the MOSFET.